Okay, good morning. So, let us do a recap of what we learned yesterday. So, yesterday we started learning about hard and soft magnetic materials, and the reason for materials being hard or soft is coming from anisotropy. So, I told you that if you measure a property and if it depends on direction of measurement, then we say it is an anisotropy. Okay. For example, you measure the magnetic property of the material by applying field along this direction or along this direction, the hysteresis loop is going to be different. So, the properties you get like MR, MS, MS is the same, okay. MR, coercivity, all these are going to be different in different direction. Then we say that there is a magnetic anisotropy. So, we learned about a few different magnetic anisotropy. Firstly, I introduced magnetocrystalline anisotropy. Yeah. Oh, okay. Maybe this one is hitting. Sometimes this one hits the mic. Okay. So, first type we learnt is magnetocrystalline anisotropy. So, if the magnetic atoms like cobalt, they are in certain crystallographic structure like hexagonal closed pack structure, then the EZ direction is along the C axis. Okay, we haven't learnt about what is hexagonal closed pack structure, what is C axis and so on. Maybe today we will do that. Okay, after we finish the remaining parts of magnetism, let us do that. Okay, time being, you imagine that let us say, okay, basically A, B axis are in the plane, C is in the vertical direction, okay, of the unit cell. So, there is an anisotropy EZ axis along the C direction. So, this is something that we learnt. Secondly, we learnt about interface anisotropy. So, instead of having a bulk very thick cobalt layer, let us say you interface cobalt with platinum. So, you split it into many layer and interface cobalt with platinum, for example. So, in this case we can see a perpendicular magnetic anisotropy. Typically, a cobalt film will have EZ axis, I mean EZ direction of magnetization in the plane, but if you deposit multi layers of cobalt platinum, you can get a magnetization in the perpendicular direction. So, we can say there is a perpendicular magnetic anisotropy setting in because of the interfaces. So, this is one type of interface anisotropy. The second type we learnt that if you bring a ferromagnetic material in contact with an antiferromagnetic material and come up with some recipe. So, after you make this film according to this recipe, you will notice that the hysteresis loop is shifted from the origin by a certain field value. So, we call this exchange bias field or HEB. Okay, so, in this case you see a shift, and you also see that the hysteresis loop has only one remnant state. Okay, so, this is also called unidirectional anisotropy. So, imagine that I have something like this. Okay. So, let us say imagine there is some grip which holds this pen either towards left or right. Okay. So, this grip holds the pen either towards left direction or right direction. Okay. All the other directions are unfavorable. That is what happens in the normal ferromagnetic material. So, you have two easy directions. So, it can be either this way or it can be the other way. Okay. But in the case of these systems where you have unidirectional anisotropy, only one direction is favored. Whatever I do, let us say I apply something, then it will come back to the same direction. So, only one easy direction. So, in the absence of any magnetic field, the magnetic moment is going to point only in one direction. Okay. So, that is why this name unidirectional anisotropy. Okay. Now, let us move on to the next part. Then we learnt about shape anisotropy. Okay. So, when I bring shape anisotropy, I can also discuss something about diamagnetism. Okay. These two are not related, but what I want to say is like all the materials, right, like even you take cobalt also has closed shells. Okay. So, the closed shells of cobalt atoms also will show diamagnetic property, but the diamagnetic property is overshadowed by the uncompensated spins in 3D shells. Okay. So, all the materials will show some kind of diamagnetic property, but if they have like unpaired electrons, then they will have ferromagnetic property. Ferromagnetic property will overshadow diamagnetic property. Okay. So, let me erase this whole thing. Okay, I do not want to confuse you. So, when I talk about shape anisotropy, like diamagnetism, shape anisotropy will be observable mainly in the absence of any other anisotropy. Say magnetocrystalline or some such anisotropy. Okay, when all the other anisotropy forms are very low, then we will be able to observe shape anisotropy. So, shape anisotropy determines that, let us say you magnetize a material along certain direction, the north pole and south pole must be far away. Okay. So, for an object like this, the easy direction is along this direction, this is hard. Okay. So, when you have material like this is easy direction, all the other directions are hard direction. Okay. So, the rule of thumb is that the north pole and south pole formed by your magnetization should be far away from each other. Then we also learnt about some other anisotropy. Let us skip them. So, after anisotropy, then we moved on to discuss about domains. Okay. So, we started with the Heisenberg interaction, which states that the spins have to be parallel to each other, but we cannot keep too many spins parallel to each other. That will mean that the magnetostatic energy will be larger. Okay, so, if magnetostatic energy gets very large, then the system will form domains. That means, it will have some domains with opposite magnetization, but in a system it may be random. I mean, in the case of perpendicular, like you have only up domain or down domain, but if you have in plane magnetic, I mean, if there is no perpendicular anisotropy, in the in plane the magnetization can be in any direction. Okay. So, you will form various other types of domains. Okay, the system will form domains and it will also form domain walls. Domain wall is the region where the spins gradually change the direction from one domain to the other domain. So, these regions are called domain walls. Okay, so, domain walls are formed in order to minimize, I mean, you cannot increase the Heisenberg exchange energy. Okay, so, domain walls are formed to minimize the exchange energy. Okay, when you form domain walls or when you form many domains, you are forming domain walls. Which increase two energies. One is the exchange energy, because now the neighboring spins are not parallel to each other, and it also increases the anisotropy energy, because the spins are not in the direction parallel to the EG axis. Okay, so, when we have domain, there are two kind of energy. One is the magnetostatic energy, the second one is domain wall energy. Okay, so, a system always wants to minimize the total energy. Okay, total energy has to be minimized. Okay. So, in some cases forming domains will minimize the magnetostatic energy a lot. It might increase the domain wall energy a bit. For example, by doing something, let us say you spend 100 rupees, but you gain 1000 rupees. Okay. Okay, you do some task A, you lose 100 rupees, gain 1000 rupees. Okay. You do task B, you lose 1000 rupees, gain 100 rupees. So, which one will you do? Obviously, this, right. So, the same thing. So, if the system will form domains if the gain which is like minimization of magnetostatic energy is a lot compared to the energy spent to form the domain walls. Okay. So, this is the one that determines whether domains will be formed or not. Okay. So, the transition point is actually the size of a particle. Okay. So, here for example, let us say I put the diameter of a particle. Let us imagine we have like some spherical particle. Okay. So, if the particles are bigger in size, so when the particles exceed some critical diameter, you will see multi-domain pattern. Your particles will be multi-domain. If the particle sizes are smaller, then you will have single domain. Okay, so, for cobalt for example, the critical value is around 50 nanometer, okay, roughly. Okay. Do not take this number for accuracy, somewhere there about 50 nanometer and above. If you make a cobalt sphere, the cobalt sphere will have multi-domain. Okay. But if you make the same cobalt sphere to be of say 20 nanometer in diameter, then you will see that cobalt sphere is a single domain. Okay. So, I showed you this using the MFM images. So, I showed you the data of a tiny disk made by lithography. So, you saw that the bigger disks had many domains, and as we shrink the diameter of these tiny cylinders to 15 nanometer and below, we notice that they have single domain property. Okay. So, this is something that we learnt yesterday. After this, we started learning about magnetization reversal mechanism. Okay, the word may look very complicated. Basically, what it means is, if you bring a magnet next to a magnetic material, how the magnetic material will respond. Okay. That is basically the magnetization reversal mechanism. So, I mentioned that in some material only the region directly in the vicinity of the magnet will reverse the polarity, and in some material the reversal will spread over to very large distances. Okay. So, I mentioned that both possibilities can happen. Okay. So, when this happen, so when there is a domain wall motion, reversal mechanism happens, then you will see that your magnet influences a large region of the magnetic material below it. And this happens when you have single domain particles. So, I mentioned to you that quite often, usually whatever material you prepare, let us say you make some thin films, or you make powders, you combine them to make say some piece of magnet, okay, bulk magnet. Okay, so, in all these cases usually you will find this domain wall motion reversal mechanism. So, this is the usual case. Okay. Quite often you will end up seeing this one. Only when you do some special treatments, for example, you do some chemical synthesis, you make particles, okay, you cover these particles with some encapsulation. Let us say you have some polymer or some coating, non-magnetic coating separated from each other. So, these particles do not come closer to each other, for example. Okay. Under such cases, or you make thin films where you have magnetic grains separated from each other. So, you see there is a lot of space between the magnetic grains, or let us say you do lithography, you make magnetic islands by lithography separated from each other and small, okay, all this and small. Then these particles will be single domain. So, these single domain particles will undergo coherent rotation or something called Stoner-Wohlforth reversal mechanism. Okay, Stoner is one scientist, Wohlforth is another scientist. So, they came up with this theoretical model to explain how a single domain particle will respond to a magnetic field. Okay. So, they undergo coherent rotation. So, I showed you that in the case of domain wall motion, for example, let us say this is one domain, as you apply field, this domain will spread. Okay, so, your time t1 it is like this, t2 it has spread over larger distance, t3 it has spread even larger distance. Okay. So, that is domain wall motion, and in the case of coherent rotation, your let us say your particle has many spins. So, the spins are all parallel because it is a ferromagnetic particle, and as you apply field, these particles will go reverse together in phase. Okay, they will act as one, they will switch together. Okay, that is coherent rotation or Stoner-Wohlforth reversal mechanism. Okay, so, in Stoner-Wohlforth reversal mechanism, let us say a particle is in this direction, you apply a certain magnetic field and the particle is in this direction. Now, you reverse the magnetic field, and only when you reach this point, when your applied field is equal to the anisotropy field of the particle, then the particle will switch magnetization to the opposite direction. Okay, again if you go from here to here, then when you reach hk, again the particle will switch the direction. Okay, so, this is what happens when you apply field in the easy direction. Let us say now I apply magnetic field in the hard direction. So, let us say I start from here. So, how will my path look like? Will it be a straight line or will it be curved? Curved. How many of you say curved? 1. How many of you say it will be a straight line? Okay, straight line is majority and winner. Okay, because we are applying magnetic field in the hard direction. Hard direction. Let us say this is the easy direction. Magnetization is like this. So, if you apply magnetic field in the hard direction, the magnetization will gradually rotate along the direction of applied field. So, as a result you will see a straight line. Okay. So, this straight line will meet this red curve at some point. So, which point it will meet? Whether it will meet here, here or here. How many of you say A? No one. How many of you say B? B, a few hands. How about C? C is majority, but B is the winner. Okay. So, in the case of Stoner-Wohlforth reversal mechanism, the meeting point of easy and hard direction is H k. Okay. So, at H is equal to H k, the magnetization is saturated. So, yesterday I showed you two graphs. Okay. So, I showed you two graphs, one corresponding to easy direction, another graph corresponding to hard direction. So, if you look at those graphs again, I do not know whether you got the PDF files. Have you got? No. Okay. Anyway, I said to Professor Dutta, he will send you the PDF of the slides. Okay. So, I had two graphs. So, sometime the problem is when you have two graphs, you do not know the relative. Okay. So, here you will notice that this point is H k. Okay. So, these two curves will meet at this point B. I mean this is only for isolated nanoparticle. Okay, let us say you have another system, for example, let us say you prepare nanoparticles. So, you have a lot of nanoparticles isolated from each other. Okay, these are all single domains, but now you have a collection. Okay, here you have only one isolated nanoparticle, far away from any other particle, far away from any other particle. But normally when we make any system, right, we cannot deal with one particle. So, we will have many particles. Okay, so, this is reality. So, reality is like we have a collection of particles. So, individually each of these particles is a single domain and it will follow Stoner-Wohlforth reversal mechanism. But when you have a collection like this, there are many interactions. For example, let us say this is magnetized in this direction. So, this generates certain magnetic field. So, this magnetic field will influence the neighboring particles and so on. So, when you have a collection, there is interaction between particles. Okay, so, this is a Stoner-Wohlforth system, because each particle is a single domain and they are isolated from each other and so on. But still there is some interaction between these particles. Okay, so, when you have such interaction, usually what happens is the particle may not reverse at this field. Okay. So, typically when you have a collection of particle, the coercivity at which say 50% particle switch is typically like half of h k. This is a rough number. Okay. You do not pay too much emphasis to this one. So, approximately half of the anisotropy field, 50% of the particle would have reversed. Okay. If you have only one particle, that particle is supposed to reverse only at this field h is equal to h k, but when you have many particles, like some particle reverse earlier, some particles reverse later. So, you can say half of the particles reverse at around this field. Okay, so, if I use another color to show how a group of particles may behave. So, for example, they may something like this. Okay. So, some particle reverse earlier, here some particles have reversed. So, here half of them has reversed, and at this field, the saturating field, all of them have reversed. Okay, this is a more realistic picture. Okay, we learnt that. Then what else did we learn? Then I told you about the energy landscape. So, if you plot the energy as a function of angle, so let us say this refers to one easy direction, this refers to another easy direction. The energy will be minima when the magnetization is along the easy directions. Okay. On the other hand, for any other direction, energy will be high, and along the hard direction, this is the hard direction, energy is the highest. Okay. And this height of energy is called energy barrier. And this energy barrier is given by Ku times V, where Ku is the materials anisotropy. So, it is called anisotropy constant. So, typically this is expressed in SI units, joule per cubic meter, in CGS unit, erg per cubic centimeter. So, you notice that this is energy density, energy volume density. Okay. So, this is energy per volume, you multiply by volume, you get energy. Okay. So, this KUV is the one that keeps the magnetization fixed in a particular direction. Okay, so if this energy barrier is small, you can easily change the polarity from north to south. Okay. If this barrier is very large, then you have to supply a large amount of energy to switch the magnetization. Okay. So, the coercivity of the material, for example, depends on the QUV. So, what makes a material hard or soft? Basically, the anisotropy constant. Yes. Yeah.
This energy diagram is for those interacting nanoparticles, or
This one is for isolated particle. Yeah. I mean, when you have lot of particle, then there is also another field coming in. So, it will be KUV minus some field term which is proportional to the internal field. So, every particle will see a magnetic field from the neighbors, and the energy corresponding to that field will be subtracted from KUV.
but if those like isolated nanoparticles are interacting, so like some field is acting on them, so long range order can sets in. Like
No, I mean when I say some field is acting on them, it is coming from the neighboring particles, because neighboring particles have certain magnetization, right. So, they will generate a stray field.
that internal magnetic.
Yeah, internal magnetic.
Sets in order. Like, but I understand this energy diagram is like for super paramagnets. So those nanoparticles which do not interact with each other.
Okay, superparamagnetism is another case. I mean, this is for any isolated particle, you will have this one. I mean, when you have isolated particle, this energy barrier is KUV. When you have interacting particle, there will be a second term. Later, when I show the slide, I will show what exactly is the term, but is some maybe m dot h or something like that. Okay. So, some energy term here that will reduce this energy barrier. So, when you have interaction, this height may be reduced a bit. Okay. So, this reduction in the height is coming from this internal field term. Okay. So, when we talk about superparamagnetism, we are talking about the competition between KUV and the KBT. Okay, at room temperature, we have thermal energy, which is the temperature in Kelvin multiplied by Boltzmann constant. So, when this thermal energy competes with KUV, then you have superparamagnetism. So, superparamagnetism happens when the volume is very small. Okay. So, when the volume is very small, for example, your KUV also is going to be lower. So, when you have very small particles, your KUV is small. Okay, the energy barrier itself is lower. Energy barrier is lower, then thermal energy starts competing with them. As a result, the magnetization of the particle is not constant as a function of time, it flips with respect to time.
So, the particles are interacting there.
In the case of superparamagnetism, the particles can interact, but at any point of time, let us say you have many particles, right. So, this particle may have magnetization in this direction, another one like this. There will be interaction, but I think it will average out unless like the other cases. So, because of this randomness in the direction of magnetization of each particle, you will see that there is no hysteresis loop. Okay. So, superparamagnetic particle will have no hysteresis loop. So, they will they will saturate, because even though the particles do not have a constant magnetization as a function of time, they still have magnetization. I mean, each particle have certain magnetic moment, because this is still ferromagnetism. So, within this small particle the spins are all parallel. So, when your applied field is very large, you will saturate all these particles along certain direction. So, they will saturate only when there is no applied field. So, in the absence of any magnetic field, the only interaction is between these two energies. So, thermal energy will make these particles to fluctuate. Mm-hmm.
The landscape is for isolated single domain particles.
Which one?
The energy landscape is
Yeah, this landscape, the orange one I draw was for the single isolated particle. So, when there is interaction, there will be this green curve, we can say. Okay, so basically this is what we learned yesterday. So, let us go through some more items, then we will have some questions. So, here I tried to show how the switching will happen. So, this is a video. So, many things happen in this picture. Okay. So, here we have magnetization and the field. So, if you look at this particular image, you will see the magnetization and the field. Here you will see the energy landscape, and here you will see the hysteresis loop. Okay. So, all aspects of Stoner-Woolford is summarized in this video. So, basically you increase magnetic field. So, you can see that the magnetic field is increased from this to this angle. So, you can see that the energy landscape changes. So, this dotted line is the energy landscape in the absence of a field, but as you increase the field, you are changing the energy landscape. So, magnetization pointing along the direction of field is more stable, that is here. The other direction where magnetization is opposite to this field is unstable. Okay. Now, we are reducing the field. So, you can see this line getting shorter, this black line getting shorter. Now, magnetic field is 0, black line is somewhere here. So, we are at this point again. Now, magnetic field is going in the opposite direction. Okay. Magnitude is small. So, when this line meets here, that is H is equal to Hk. Okay. So, when this black line is here, that means the applied field is equal to anisotropy field. Okay. You can see that the reversal has happened. So, now you see this one has come here, magnetization has changed direction. Now, magnetic field is 0, now magnetic field is Hk. So, reversal has happened. Okay. So, I will play again, once again you can watch everything again. Okay. So, when you have many particles, single domain particles, so you can notice that as the field increases, when this field is more than the anisotropy field of certain particle, then that particle will reverse. So, in a group of particles, each particle will reverse at their own field. Okay. So, you can see that they do not switch together. So, they will switch independent of each other. Okay, so this is a cartoon of what happens when you have Stoner-Woolford reversal mechanism. So, at a very high field, all the grains are saturated in one direction. When you come closer to remnants, a few of them have switched. When you are here, a few more have switched. At coercivity point, like half of them have switched, and so on. Okay. So, this is how the reversal of particles happen when they are single domains. Okay, let us do some questions now. Same as yesterday. So, it is spin week 2. So, go to wooclap.com and use the code spin week 2. Okay, majority of you are right. So, when we have isolated particles, we will have coherent rotation or Stoner-Woolford reversal mechanism. Okay. Next question. Okay, how many of you are taking notes on the paper? Okay, majority of you, very good, very good. So, I can find out whether you are taking notes or not from this question. Okay. Yeah, many of you are taking notes. Okay. Yesterday I told you that the HK oops, so 2 Ku over ms. So, if you have taken notes, you would have answered this correctly. Okay. So, many of you are right. So, HK mainly depends on 2 Ku. It is inversely proportional to ms. So, this is wrong. So, 4 of you are not taking notes. Okay, so that is about magnetization, the magnetism basics. So, on 15th May we did not have time to cover this one. So, I told you that I will give a brief introduction to the material science, so that you can follow what I am going to talk in the next few weeks. Okay. So, we will do that first, then we will go on to the next chapters. Okay, materials form the era. So, you know that there is bronze era, copper era, stone era, iron era and so on, right. So, materials have played an important role in determining the way in which we live, the technology and so on. So, materials belong to various types. So, it can be metals, it can be ceramics, glasses, polymers, composites, semiconductors and so on. Okay. I mean, in the earlier days people had like only one choice. So, during the bronze era they have no access to say stainless steel or something like that. Okay. But now in this era we have access to lots of materials, and we will choose a material for a particular application depending on the performance that we want and also the cost. Okay. So, for example, to carry water you either use plastic or stainless steel, you do not use gold, right. It is very expensive. Okay. So, depending on the cost and the intended application performance, we choose different materials. Okay. So, materials belong to two types in terms of the atomic arrangement. So, one type is called crystalline. So, in many materials like metals, the atoms are arranged in certain order. Okay. So, for example, let us say these blue circles are atoms, they are arranged in a certain order. So, this periodic arrangement is what we call as lattice. Okay. And there is also long range order in some material. For example, I look at the atoms in certain place, I move several centimeter away from that location, I look at the atoms again, and if they are like almost same, then we can say that there is a long range order. So, the other type is basically non-crystalline materials or amorphous materials. So, glass, silicon oxide, these are some examples of non-crystalline materials. So, in non-crystalline materials, these atoms are not arranged in order. So, you notice here the atoms are disordered. you move further away, again the arrangement is not systematic. Okay. So, you will find a disorderness in non crystalline materials or amorphous materials. Okay. So, you cannot classify amorphous material because they are random. Okay. There is no way you can define some randomness, right. So, it will be very random whether you look here or look there, but crystalline materials have been classified into 7 crystalline systems and 14 lattice types. Okay. So, the 7 systems are cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic and triclinic. Okay. So, even I do not remember all of them, but I just want you to focus your attention on cubic and hexagonal. Okay. Because in this course you will be dealing with hexagonal crystalline structures and cubic structures. Okay. So, if you remember when I taught you magnetism, cobalt, I told you that cobalt atoms are in hexagonal structure. Okay. So, hexagonal and cubic are most relevant to this particular course. So, like me, you do not need to remember everything. Okay. So, this is how they have been classified. So, in cubic system, as you know, in a cube all the sides will be the same. So, A is equal to B is equal to C, and the angles alpha, beta, gamma are all 90 degree. So, this is the convention we use. So, we have A this direction, B is here, C is there, then alpha is the angle between B and C, beta is the angle between A and C, gamma is the angle between B and here. Okay. Gamma is here. So, this is a cubic system. So, in tetragonal system is very similar to cubic, only thing is you stretch a bit. Okay. The C is longer than A and B. Okay. All the other things are same. So, it is like if you place 2 cubes one top of another, you can say it is a tetragonal. Okay, because the C is now 2 times A. So, A is equal to B, but not equal to C is the definition for tetragonal. Orthorhombic, A, B, C all are different. Okay. The lengths are all different, but the angles are all 90 degree. Okay. So, like that you can do various types. When you come to hexagonal, you see this is how the hexagonal crystal will look like, but we take one slice. So, we take, let me draw. Okay, we just take that one slice. So, that slice will look like this. So, the A is the same, that means this length and this length are the same. C, which is this one, could be different. C is usually longer than A. And if you look at the angles, gamma is 120 degree. Okay. So, this angle, so at the bottom you have this, right. I am just looking at this one. So, this angle will be 120 degree. All the other angles are 90 degree only. Okay. So, just remember that we will be using. Okay, let me move to the next slide. Okay, so, these are basically the 7 crystal lattices, and you can expand it further depending on more complex arrangements. So, in simple cubic you have atoms only in the corners. Okay, in body centered cubic you have atoms in the corners, and in addition you have one atom in the center of the body of the cube. So, that is why the name body centered cubic Okay, so we will be using this name quite often, BCC. BCC means like you have 8 atoms in the corner and 1 atom in the center of the cube. Okay. Then we have another type of cube which is face centered cube. So, in this case you have 8 atoms in the corners, and in addition you have, I mean, a cube has 6 faces, right. So, in each face, the center of the face of the cube, you have 1 atom. Okay. So, face centered cubic means, let us say this is the face of a cube. Okay, you have 1 atom in the center. So, 6 faces, you have 6 atoms. Then hexagonal we already learned. So, for this course you will be looking at this hexagonal, face centered, body centered. We need to know these 3. So, in one another perspective, if you look at the hexagonal closed pack structure, you will have 7 atoms including the center atom. So, this is what we call A plane. The next plane you will have like 3 atoms, then next is similar to A. Okay, so, you will be stacking atoms like this. So, if you look at this one, so you see there are 7, right, this is another 7, but you will see 3 coming from the neighboring hexagonal structure. Okay. So, there will be A, B, C like that. So, this is A, this is C, then there is one plane coming from the neighboring hexagonal structure. Okay. So, when we talk about hexagonal structure, we say AB arrangement. Okay. FCC also is very similar, except that you have A, B, C, A and so on. So, it will have A, B, C kind of arrangement. Okay, let us do some question. Okay, let us not do question. Okay, not important. So, how can you check whether a material is crystalline or amorphous, or what kind of phase it is in? So, typically we use this device or this technique called X-ray diffraction to check whether a material is a crystalline material or amorphous, or in what kind of phase it is in, and so on. Okay. So, X-ray diffraction measurements are carried out by looking at Bragg peaks. So, we calculate the information about the crystals based on Bragg's law. Okay. So, do you know who is the youngest Nobel Prize winner? Huh? For physics. Not for the Peace Prize, but the physics. For physics, the youngest Nobel Prize winner is Bragg. Actually, this Bragg is two Braggs, Daddy Bragg and son Bragg. Okay, so son Bragg also got Nobel Prize. Okay, so they explain the X-ray diffraction based on the interference and the diffraction. Okay. So, you shine X-rays onto the crystal planes So, there will be diffraction and there will be interference of the X-ray wave fronts, and based on this periodic arrangement, let us say the wave front that hits this plane and goes here, and this wave front, if they are in phase after this difference. Okay. So, this difference 2D whatever 2D sin theta will make the two wave fronts to be in phase. Okay. Then there will be constructive interference. Okay. So, when this condition is met, when n lambda is equal to 2D sin theta, constructive interference will take place and you will find peaks. Okay. So, when you do XRD, you will find there will be some peaks. Okay. So, if you know the lambda you know, because that is the wavelength that you used in the X-ray system, then you know the peak positions. So, these are 2 theta. So, you divide this angle by theta, you get divide by 2, you will get theta. So, substitute them, you can calculate the lattice constant d. Okay. So, for doing XRD, usually we use this 2 theta configuration. That means, your sample is somewhere here, the crystal planes are here, the incident angle is theta, the refracted angle is also theta. So, in this picture you will see that there are some numbers within curly brackets, okay, 1 1 1, 2 0 0, 2 2 0 and so on. So, these numbers represents the planes which causes this diffraction and interference to happen. Okay. So, let us say this particular plane, set of planes is what gives rise to the peak here, then we have a name for it. Okay. So, those numbers are called Miller indices. So, it was proposed by this scientist William Miller. Okay. So, these Miller indices are calculated based on the reciprocal of the intersection of the plane within the cell axis. Okay. For example, let us say this is the origin. So, imagine a cube. So, the origin is somewhere inside, not in the outside, somewhere here. So, with respect to that origin, we have x, y and z directions. So, let us look at this yellow plane. Okay, this yellow plane is meeting this yellow plane is meeting x at 1, it is meeting y at 1, it is not touching the z at any time. Okay. So, we can say it is touching z at infinity. Okay. So, these are the points of intersection. Okay. So, first we write the intersection 1, 1 and infinity. So, we are talking about this plane, this yellow plane. Okay. So, the reciprocal of this will be 1, 1, 0. Okay. So, this yellow color plane, plane 2 is actually 1, 1, 0. So, similarly, you take plane 1 is meeting x at infinity, it is meeting y at 1 and it is not touching g. So, infinity 1 infinity. So, reciprocal will be something like this. Okay. So, plane 1 is 0 1 0. So, this is how we derive the Miller indices. So, when we talk about XRD, the normal brackets indicates crystalline planes and the square brackets indicate directions. Okay, we can also do transmission electron microscopy and even look at the atoms. So, here you prepare a thin piece of sample around 10 nanometer in thickness, so that electrons can go through and you can use electron as a electromagnetic wave. I mean electron is the wave for doing microscopy. So, you can look at atoms. So, in this case you can see the atoms. Okay. Okay, so you can use many techniques like XRD transmission electron microscope to know about the crystal property of materials. That is one thing. Secondly, as we discussed 2 days ago, the crystal material. Yes.
Can we see the atoms or can we see the planes?
We can. I mean, if your microscopy skills are good, microscope is very good, we can see the atoms. So, in the previous picture you can see all these white dots.
They are the satellite points and not the satellite points.
Pardon?
They are not the satellite points, right? They are the atoms only.
They are atoms, yes. Okay, so on day 2 we also discuss about single crystal, polycrystal materials and so on. So, the difference is, in the case of single crystalline materials, there is a long range order. So, as I mentioned, I look at some atoms, they are in certain arrangement. Sorry, my drawing is not good. So, they have certain structure, then I go like several centimeter away, then they look same. That means, the order is extending over several centimeter or hundreds of millimeters. So, that is what is called single crystals. Okay. When we talk about polycrystalline material, so within certain region there is certain atomic order. Okay. So, there is some lattice within this region. So, it is crystalline, but if you go to another region, again it is crystalline, but they are in a different direction, maybe now they are like this. So, it is like the domain concept that we learned. So, we can say that this is like crystalline domain. Okay. Within small region there is a periodic arrangement, you go slightly far, there is another tiny crystal where the periodic arrangement is slightly tilted and so on. So, we have many tiny crystals. So, when we say polycrystalline, we are talking about many tiny crystals, and for this we use the term grains. So, in polycrystalline materials we have many small grains. So, within a grain itself is a small crystallite, you have atomic arrangement in a lattice, but these grains do not extend over large range. So, there is only short range. Okay. So, for some applications single crystals are used. So, many applications polycrystalline materials are also used. Okay. So, this picture shows you the difference between single crystalline, polycrystalline and amorphous material. Amorphous material, the atoms are not in any order. So, there is randomness, there is no lattice. In crystalline material there is lattice, and this lattice spreads over very large distance. In polycrystalline material there is lattice, but you can see that there is one region, then there is another region and so on. There are many tiny regions which we call grains. So, in this picture, except the white region, all the other regions are grains. So, tiny crystals like this. Okay, so, basically the polycrystalline materials will have many tiny regions. So, each region there will be periodic arrangement of atoms and there will be some grain boundary. So, these are the boundary between the grains. Okay, that is all you need to know before we move on to the next lecture. Is it time for tea or? Okay, we can break now. Yeah, you can say that the energy by very small plastic, yeah, definitely. Unlike paramagnetism, yeah, paramagnetism you need that. So you are saying your particle, I mean what I am talking is a general picture. So for most general particles, the superparallelism K is for which particle? No. I mean this Ku is a material property. For example, let's say let me list the Ku of different materials. So some of the highest Ku materials are selenium, cobalt, iron, platinum, iodine, platinum, neodymium, and boron. So these materials have like a 10 power 6 cubic meter and so on. So if you take say some cobalt core kind of material, they will say like 5. Then some other materials can be much lower. These are permanent diamonds. Yeah. The Ku is yeah. I mean Ku will only reduce when you see the size because so in bulk you have so many atoms, right? The surface effect doesn't come into picture. But if you make the grains to be very very small, then some of the atoms in the boundary they don't have atoms, right? So there will be some surface effects, and when you go to very small size, Ku is going to be only reduced. So this we can say that these are the values of Ku of materials, and we can roughly say that it's volume independent. Okay. So when you are reducing volume, this Ku
KU doesn't change. So KU is fixed almost, and your volume is reduced, so KU is reduced. So you are going this direction only. I don't know.
Why? Okay. I have to check.
I haven't come across. So I'm not sure whether this is an artifact or not. I don't know if you have checked. So how do you measure hysteresis?
VSM or like
Okay. How do you do the slope correction, the background correction? You put your sample onto some rod, right? So what is this rod made of?
it's magnetic.
Dynamic. Okay. So when you actually measure, you might be seeing something like this. Then you correct it to get it right.
Calibration is done.
Yeah. So you do the correction, right? So from this you bring to this. So in this correction, there could be errors. You may be over correcting, you may be under correcting. So all this may give rise to this slope. So you have to be very careful that the slope is coming from slope correction. I mean, in theory, superparametric materials should support. They are supposed to saturate. Let me change the date. I don't know why that.
ಸಂಜೆ ಫೋನ್ ಮಾಡ್ತೀನಿ. ಅದೇ ಸಂಜೆ ಫೋನ್ ಆಯ್ತು ಹೇಳ್ತೀನಿ. ಈ ಕ್ಲಾಸಲ್ಲಿದ್ದೆ, ನಾಳೆ ಸಂಜೆ ಕ್ಲಾಸ್ ಮುಗಿದ ತಕ್ಷಣ ಫೋನ್ ಮಾಡ್ತೀನಿ.
Okay, let's continue. As I said on day 2, magnetic recording is the field from which spintronics grew. Okay. So, many of the inventions from magnetic recording gave rise to the spintronics phenomenon, and the magnetic recording is the one area where spintronics was first applied. Okay. So, we are using spintronics based reed sensor for reading information in magnetic recording. So, just for 1 or 2 sessions we will touch on magnetic recording. before we move on to hardcore spintronics. Okay, so, for the next few minutes we will focus on magnetic recording. Magnetic recording was first invented in late 1890s. Then people started using magnetic recording for audio, so for recording voices. Okay, then somewhere in 1950s, particularly 1956, IBM came up with a hard disk drive for mainframe computers. Okay. So, this was in 1950s. Computers were used in mainframe computers. Then somewhere in 1980s, desktop personal computers became popular. So, hard disk drives were invented for desktop computers. Then laptops started using hard disk drives. Then, as I mentioned a few days ago, Apple introduced iPod, a music player with a hard disk drive for music files. So, we could play like thousands of songs using one device, which was revolutionary at that point of time. Then gaming applications like Xbox started using hard disk drives. Then somewhere in 2005 later on, social media applications like Facebook, YouTube all came into picture. So, they started storing information. Now, we use cloud and personal storage and so on. Okay, so, this is how magnetic recording has been useful and is still useful. Okay, moving forward, where we will require hard disk drives. So, one application is like autonomous cars. So, you know that Tesla can drive on its own. There are many autonomous cars coming into picture. So, they have lots of cameras, they capture video. So, all these generate lot of data. Okay. So, roughly 4 terabyte of data is generated every day. All these need to be stored somewhere. So, that is one application. And if you look at this video, in other ways it should work. Yeah, okay. Not playing. Okay, maybe I play another video. Not here, another video. Okay, let's go back to the slides. So, the video you saw is coming from a technology called True View Video Technology. Okay. It is coming from Intel. I do not know whether you have noticed in IPL 2021 or 22, there was this technology. So, you remember, I remember Suresh Raina playing some shot, and that was shown in different angles. Okay. So, in this technology what they do is like they place multiple cameras around the ground. So, each camera captures the video, then you can choose to watch which camera you want to see. Okay. So, by choosing the video from any particular camera, you can watch the game at a totally different perspective. So, imagine like having say 10-degree one camera, you have 36 cameras, and all these cameras are capturing information at 4K or 8K HD. So, they are generating lot of data. Okay. So, you want to store all this data. Okay. So, future it is going to be like everyone is going to generate data, and we need some device to store information, and solid state drives are more expensive. Hard disk drive is the cheapest way of storing information. So, that brings us into why we need to learn about magnetic recording. Okay. So, today we will learn about some basics of data storage. So, quite often there will be many new terms. So, I need to bring some analogy to introduce the data storage concepts. So, here I will use book as an analogy, because book we store information, right. So, it is a data storage, not electronic device, but it is a system that stores information. So, the magnetic recording people will always use the word medium or media. So, basically when we say medium or media, that is something where the information is stored. Okay. When we say medium or media, that is the place the information is stored. So, if you take book as an example, so in book we use paper to store information. So, paper is the medium, and any data storage system that you create should be able to store information, and we should be able to write information. Okay. So, there should be some ways to write information. So, in the case of paper or book, we use ink to print, or we use pen to write information, and there should also be some ways to sense the information. Okay. Otherwise, how do we know that there is information? Okay. So, there should be some ways to sense information. In the case of book, we use our eyes to sense information. Okay. It is not enough. We should also have some ways to interpret the information. Okay. So, you can look at all these letters, you can read information and interpret what I have written here. So, you have been trained to read English, and your brain has been trained to read English. So, you know. Okay. But if I show you something, then you do not know, even I do not know what it means. Okay. Because we have not been trained in Chinese. Okay. So, all these are important. So, when you talk about a data storage system, we are talking about having a medium to store information, we are talking about some ways to write information, we are talking about some ways to sense information, and there should be some ways to interpret the information. So, you have a data storage device, you have a computer. So, the information has to be passed from the data storage device to computer in a meaningful way, okay, in an interpretable way. So, typically this part of magnetic recording is done by electrical engineers and mathematicians. So, they do some coding, signal processing, mostly mathematics with some electrical engineering concepts to interpret the information. So, we will not learn about this. We will also not spend too much time on how do we write information, particularly when it comes to magnetic recording. But when we are talking about memory, MRAM and so on, we will be learning about all these concepts. How do we store information, how do we write information, how do we sense information, we will learn all this when we learn about MRAM. But when it comes to hard disk drive, we will not spend much time here. We will spend more time on how do we sense information, because this is based on Spintronics principle. But I will give you some brief idea how do we store information in the hard disk drives. Okay. So, I will be showing this triangle quite often, almost every day I will show this triangle. Okay. From now, every day I will show this triangle. So, we will be talking about how do we write, read or store information. So, in the case of book, we use pen or pencil to write information, we sense information with our eyes, and we store information on paper. Okay, so, if you take rock carvings, for example, we use nails to write information, we use our eyes to read information, we use rocks to store information. Okay. That brings us to the book lab part. Yeah, please scan. Okay, let us go move on to the first question. Okay, so only 10 of you are right, okay, and the correct 10 is this. Okay, so none of these which I have listed belong to magnetic recording. So, quite often people think that CD is magnetic recording or flash is magnetic recording. Okay, so first I want you to go away with the knowledge that none of them is magnetic recording. So, if you take CD or DVD, for example, we have a disc. So, in that disc we have some material. So, that material has the property to go from amorphous to crystalline or crystalline to amorphous. So, we just learnt about amorphous and crystalline materials, right. So, this material, for example, if you heat them slowly and cool slowly, you will have crystalline structure. If you heat them and cool rapidly, it will become amorphous. Okay. So, by the way in which you heat and cool, you can transition between amorphous and crystalline phases. So, the reflectivity of the material will be different in the crystalline and amorphous phases. So, we use the laser induced heating to write information. So, we can go from crystalline to amorphous, amorphous to crystalline. So, we can call one of them as 0, another one as 1. So, we are talking about digital recording. So, from now we are talking about digital recording. So, we are only looking at bits 0 and 1. We are looking at 2 states, only 2 states. Okay, so, this can be 0, this can be 1. So, we can use the reflectivity. So, one of them will be reflecting more light, another one will reflect less light, or you can look at the phase change and read information. And storing is based on, I mean these 2 states are equally stable. So, if you reach here it will be stable, if you reach here it will be stable. So, you can store information. And somewhere in 1990s we had also magneto-optic recording, which is also not magnetic recording. And if you take solid state drives, they are using semiconductor technology. So, we are using the presence of electrons or absence of electrons inside a potential well to define 1 and 0. So, those are all not magnetic recording. So, when we talk about magnetic recording, we use these principles which I show in this picture to achieve magnetic recording. Okay. So, when we talk about writing information, we have an electromagnetic head. So, we learnt about electromagnet on day 2, right. So, I showed you that if you have a coil, you send current, you produce magnetic field, and if you have a coil and you place a magnetic material. So, in this case the blue color one is the magnetic material. So, that magnetic material will enhance the magnetic field, and we can generate magnetic field from this head. Okay. So, you can see that the blue lines are all magnetic fields. Okay. So, we can use these magnetic fields to write information. So, writing information is basically keeping the magnetic moments in one direction or the other, okay, something like this. So, we use an electromagnet to write information. So, in hard disk drives, these electromagnets are in nanometer scale. So, for example, this gap may be a few tens of nanometer, maybe 50 nanometer or even less. Okay. I am not very updated on what is the gap, but it is 50 nanometer or smaller. Okay. So, we are talking about tiny electromagnetic heads to write information in hard disk drive. And for reading, we are going to look at the magnetic flux that comes out of the hard disk drive. Okay. So, we have written some information. We have magnetized the material, it's in certain direction, they produce magnetic flux. So, we sense this magnetic flux as a way of reading information. Okay. So, for this purpose we will be using some magneto-resistive sensors. So, these are Spintronics read sensors. Okay. So, we will learn about how they work later, but we use these sensors to read information. And for storing, we are using the coercivity. So, you know that once you magnetize certain material, the coercivity or the anisotropy energy keeps the magnetization in certain direction. So, once you have magnetized material with the north pole here, south pole here, we have learned that they will be stable for long period of time, and we are using this KUV to store information. Okay. So, this is how the magnetic recording works, and this is how a hard disk will look like, hard disk drive. So, if you open a hard disk drive, on the back side you will see something like this, on the other side there will be a cover, you open, then you will see something like this. Okay. So, on this side you will see a disc. Anyway, so this is the disc. So, this is the disc that stores the information, and here you will find the head. This head is the one that reads and writes the information. Okay. So, as I mentioned, the disc will be rotating and the head will be going between the inner diameter and outer diameter. So, it can read or write over the whole disc. Okay. So, this voice coil motor is the one that will make this one to go in this direction, and this motor, this spindle motor is the one that will make the hard disk to rotate. Okay. So, we have the disk, and this disk is the one we call medium. So, this medium is the one that stores the data in hard disk drive, and this head is the one that reads or writes the information. And these chips that you see from Marvell or LSI, they are like the brain of the hard disk drive. Okay. So, basically we have some magnetic flux coming out. The magnetic flux is converted into some electrical signal by the read head. Okay. So, these electrical signals come to these chips. So, these chips convert the electrical signal into meaningful information. So, the computer understands 1 or 0, right. So, this these processors are the one that will receive these electrical signals and pass them as 1 or 0 to the computer, so that your CPU can process that information. Okay. So, this is a brief outlook of the hard disk drive. So, let us watch this video and answer one question. Same video, you have watched this video before, but question is different. Okay. Okay, you may watch the video again. Okay, now answer this question. Okay, majority of you are right. Okay. The correct answer is magnets stick to the edges of a long magnet. So, what does that mean? So, when you stick many magnets together, so you can call that as a long magnet. Okay. That is what I have said. Okay. So, when magnets stick to the edges of the long magnet, what does that mean? It does not go and stick in the center, right. So, what does that mean? So, that means the magnetic field is stronger near the pole. Okay. So, when you have magnetic materials, let us say you magnetize them once. So, they have a pole. So, they have north pole and south pole after magnetizing, then they generate a magnetic field, and this field is stronger near the poles. So, if you count the number of lines per given area, you will find more lines here, more lines here, same area you will find less lines here. Okay. This means the magnetic field is strong here, the magnetic field is weak here. Okay. So, this is the reason why that particular assembly of magnets, the magnet go and stick here, okay, here or here, because the magnetic field is stronger there. Okay. So, in hard disk drive, we are using this magnetic field that comes from the poles of the magnetized material to read or sense the information. Okay. So, this is the principle of reading. How do we read information? Basically, we are relying on the magnetic field generated by magnetized material. So, once you magnetize material, they will have a certain pole, north pole, south pole, and they will generate a magnetic field, and we are using those magnetic flux lines to sense the information. Okay. So, let us do another question. So, here I have two magnets. So, you can imagine that one of them is north, another is south. Let us say blue is north, red is south. Okay. So, I have arranged two magnets in three different configuration, okay, A, B, C. So, which okay, let us say I bring some sensor to sense information. So, this sensor will look at the flux lines and give me information where the flux is more. Okay. So, we have three different configurations A, B, C. Okay. I have used this color code to represent the poles. Okay. Now, tell me which configuration will generate the least magnetic flux. Okay. I will open this question. Okay, majority of you are right, very good, happy to see that. Okay, when you have magnets with opposite poles next to each other, what will happen? They will just stick together. Okay, so, when you bring them closer, they will just stick, there will be no flux coming out of this configuration. Okay. On the other hand, when you keep say south and south, or north facing each other, they will repel. So, basically the magnetic field produced by this pole, they will all go up, okay, or down. So, you will have more magnetic flux coming out when like poles are facing each other. In this configuration, they will just get attracted, nothing will come out, no magnetic flux will come out. This sensor will not see any flux. Okay. So, normally I carry magnets, I can demonstrate this, but when I travel I cannot carry, because sometimes they do not allow to bring magnets. Okay. So, you can do experiment, you have two magnets and find out some way to sense. Okay. Okay, so, this is the principle that we used for sensing information in some very old technology. Okay. So, we used a recording technique called longitudinal recording technology for many years, and in this configuration the magnets are placed parallel to the disk surface. So, we use this kind of disks to store information. Okay. So, when the magnetization of the material is parallel to the disk, then we call it longitudinal recording. Okay. So, in this configuration, as we just learnt, when you have two north poles facing each other, there will be magnetic flux, two south poles facing each other, there will be magnetic flux, and when you have two opposite poles facing each other, there will be no flux. Okay. So, now I am talking about a very old reading scheme. So, in this reading scheme, what they do is like, I mean, in computer you have clock pulses, right. So, there is a clock tick here, here, here and so on. So, there is a window between two clock pulses. So, during these two clock pulses, if the sensor sees some magnetic flux, okay, there will be some output voltage, and we call that as 1. So, during this window again there is some magnetic flux which will result into some voltage in the sensor, we call it 1. So, during this window there is no voltage, so we call it 0. So, here again the sensor gave voltage within this window, so we call it 1. Okay. So, this is how we read information in hard disk drive. So, the reading is based on the magnetic flux that comes out of the recorded bit of the recording media. Okay. So, I cannot bring magnets, but I can play this video to show what happens. Okay, so, here you see I have stacked magnets. So, when they are sticking to each other, you know that this is north south, right. So, north south, north south, north south, something like this. Here I cannot bring them close to each other, because these are like poles, they repel. So, there is some distance here. So, this is a like pole. Here again is like north north, something like that. Let us say this is south south. Then here is north south, north south, something like that. Okay. So, now I have this kind of sensor, So, this sensor can give rise to some light. If it, can you see a red light? Okay. So, if it sees a magnetic flux, it will show some light. Okay. So, depending on the polarity, it will show red light or green light. Okay. So, I move this sensor over this arrangement of magnets. So, you can imagine this is like bits of a hard disk media. Only difference is now these are like 2 centimeter long. Okay. So, in this demonstration your bits are sorry. In this particular demonstration, your bits are 2 centimeter long. Do anyone know what is the length of a bit in current hard disk technology? Any idea? Guess some number. Huh? Nanometer, yes. How many nanometer? Okay, around 12 nanometer. Okay. So, in current technology, the length of one bit is 12 nanometer, but I am using a 2 centimeter magnet to demonstrate the concept. Okay, so, you are looking at the action in a bigger scale. Okay, so I am moving the sensor. Why? What is happening? The video is not playing. Because of the one drive, I think. Pardon?
They are if I allow accessibility.
What is it?
Yes, sir, this one. This is
Allow access. Oh, okay.
now it can play. Try playing it now.
No, only sound is coming. The video is not playing. I mean, if I download, it can play, but.
The Firefox preventing the site.
Pardon?
It's showing the Firefox preventing the site from opening.
Allow pop-ups. Okay, so maybe I need to allow the access. Yesterday the videos played, right?
Very
Nothing is coming. Is it because of the browser or no?
We can download and play it, sir. Just go to the set. We can just click and we can download it.
You mean download the video?
Yes, sir. That will do. We can download and we can play this. Copy and paste in desktop. Desktop, sir. We'll go to desktop.
No, we cannot copy paste. Let's see whether it plays like this. No.
You see the training options we are getting. Can I see one, sir?
I mean, in my computer it will play. But then the VooClap will have problem.
For videos we can do offline or
Okay. It's still downloading. Is it like this computer may miss some player with it?
that can be
Mm.
the player it want to play is missing. That can be a possibility.
Yeah, it's a MP4 player, MP4 file only. Yeah, here it's working. Yeah.
So for any, if videos are not playing, then we can go offline or both are online.
So, this video is to demonstrate that the magnetic field will be seen only at the edges of two poles. So, when I have the sensor near the edge, there is light, no light, then only this edge you see the light, right. So, this is for this concept that the field is stronger near the poles. Okay. Then this is the demonstration of recording at a larger scale. So, here again I am moving the sensor from one side to the other side. Edge there will be signal, but now you see there is no signal when it comes here, red, green, no light, again edge there is light. Okay. So, you can see that when the like poles north north or south south are facing each other, there will be a magnetic flux and we read information. Okay. So, this is a demonstration of reading from recording media, and here we are talking about a technology, very old technology. Okay. This is obsolete now. So, currently we are using another technology called perpendicular recording technology. So, in this case we are using thin films with a perpendicular magnetic anisotropy. So, we can magnetize the material to have the poles upwards. Okay. So, in this case everything will give some magnetic flux and we are sensing information. Okay. Then for storing is based on the energy barrier that we learnt. Okay. Let us say we magnetize a material down and along the z direction, that is one direction where the energy is lowest, or you magnetize the material in the up direction. Okay, let us say this is the magnet and it has two easy directions. Okay, easy axis is along this bottle axis. So, magnetization can be either pointing up or pointing down, both are energetically low, and magnetization in any other direction, say pointing towards you, is a high energy. Okay. So, this energy barrier is the one that prevents the magnetization from flipping from one direction to the other direction. Okay. So, this brings to the question that you asked earlier. Okay. So, when you have many grains, when you have only one grain, the energy barrier is proportional to k UV, but when you have many grains, each grain will see some local field, and that local field will reduce the energy barrier a bit. Okay. Yes. You mean this drawing? Before one. Okay. You don't understand this one. Okay. So, in longitudinal magnetic recording, you have a film, then on the you have a disc, on the disc you have film. So, in the film you have grains. So, those grains have easy direction in the plane of the disc. Okay. So, you magnetize them either pointing in one direction or the other. Okay. Whereas, in the case of perpendicular recording magnetization, you have film, the film has a perpendicular magnetic anisotropy. So, your grains have easy axis in the perpendicular direction. So, you can magnetize these grains to have magnetization up or magnetization pointing down. So, these two are the easy directions. Okay. All the other directions are hard direction. So, that is schematically is like having north pole of a magnet up or south pole of the magnet up, something like that. Okay, so, when it comes to storage of information, this energy barrier is the one that retains the information. I do not know whether you have learnt this terminology, volatile and non-volatile. Okay, we will go back to the other one. How many of you have heard these terms, volatile memory, non-volatile memory? Electrical engineer you will know. Then anyone else? Okay, you are all familiar, right? So, volatile memory means a memory which will lose its data when you switch off the power. Okay. For example, you take DRAM, SRAM in the computer or your mobile, they store information when the power is on, and once you switch off the power, the data is gone. Okay. So, when we talk about non-volatile memory, these are devices that store the information even after you switch off the device. Okay. So, when we talk about hard disk drives or devices like MRAM, magnetic random access memory. So, all these are non-volatile devices, which means they retain the data even if you switch off the power. So, what makes these devices to retain the data is this energy barrier. Okay. So, there is an energy barrier. So, this barrier prevents the magnetization from flipping from this direction to the other direction. Okay. So, if this energy barrier is very very low, the magnetization may flip from this to this or that to that. So, the data may be lost, but if the energy barrier is sufficiently large, the data you write will be retained for long periods of time, and that helps us to achieve the non-volatility. So, you can imagine this energy barrier like let us say you have the ball in the bottom of this bucket, and if you want to transfer the ball from bottom of this bucket to the bottom of the next bucket, you have to spend some energy, right. You have to overcome this potential energy mgh, only then you can transfer the ball from one side to the other side. So, this gravitational potential energy prevents the ball from going from here to here. So, in a similar sense, the energy barrier, anisotropy energy barrier, prevents the magnetization from flipping from one direction to the other direction. Okay. So, that is what helps us to achieve the non-volatility of magnetic recording. Okay, so, when it comes to writing information, we use an electromagnet to write information. So, my classroom teaching, I usually carry this one. This is a tiny electromagnet. So, you send current through this coil, then you will produce a magnetic field along this direction. Okay, so, if I place a Hall probe which senses magnetic field, I can see the magnetic field. Let us see whether this video runs. Okay, this one works. So, you can see that I am applying certain current, then this field So, when I connected the battery, the field is 0.27 millitesla. Once I remove the battery, there is no field. Okay. So, basically by sending a current through the coil, you produce a magnetic field here, and here I am sensing that magnetic field is the Hall probe. But if I have a disk media here, for example, let us say I have some disk where I need to write information, the magnetic flux that comes out of these poles can be used for writing information. So, we are using an electromagnet to generate magnetic field, and we use that magnetic field to magnetize the bits. Okay. So, in this case, for example, so in this demonstration I arranged the magnets physically. Okay. So, I kept the magnets like this. So, that is how I arrange the bits, but in a small disk like this, who is going to arrange the magnets. So, we are not going to physically arrange the magnets, but we are using the electromagnetic field to magnetize the disk to point in one direction or the other direction. So, the magnetic field from the electromagnet is the one that is going to determine the polarity of the magnets that you saw in the pictures. Okay. So, we use electromagnets produce certain magnetic field, and that magnetic field changes the energy landscape. Okay. So, I told you that at 0 field, this is how the energy landscape will look like, but as you apply more and more field, you can change the energy landscape. So, if this field is sufficiently large, this energy barrier will become 0. Finally, this will be the only stable state. So, the magnetization will switch. So, this is one way of explaining, but you can also use the hysteresis loop. So, we are applying a field much larger than the coercivity, so that we can switch the magnetization. Okay, so, we learnt about hysteresis loop, and the hysteresis loop parameters are related to the 3 concepts that we learnt, right. The 3 criteria are read, store, right. So, these three criteria can be related to the hysteresis loop parameters that we learnt. Okay. So, we learnt about MR. MR is the magnetic moment retained by the magnetic material even after you remove the magnetic field. Let us say you saturate, then you remove the magnetic field, you reach here. Okay. So, there is some magnetic polarity retained by the magnetic material. So, this is the one that generates the magnetic flux. Okay. So, basically if you multiply MR, the remnant magnetization of the material, by T, which is the thickness of the film. So, the MRT determines the signal for reading information. Okay. So, this part of the hysteresis loop, you can say it is related to the read property of the recorded information. Okay. So, we can say either the nucleation field or coercivity is related to the ability to retain information. Okay. So, if your coercivity is large, for example, then you cannot erase the information. Okay. For example, yesterday we were discussing about say putting MRAM into the pocket along with a magnet. So, magnet will erase the information, all those things, right. So, if coercivity is large, then your information will not be erased. Okay. If coercivity is small, the information can be erased. Okay. I can give you some example. If you take the old credit cards, so in the old credit cards you will see a black stripe. Okay. You will see a black stripe. So, this black stripe is basically a ferrite material with a coercivity of around 700 oersted. Okay. On the other hand, the magnets I have here, these are tiny neodymium iron boron magnets. Okay. So, you can see they generate magnetic field. So, these tiny magnets can generate magnetic field of around 2000 oersted. Okay. So, suppose I place a credit card on my pocket along with one of these magnets, then it is going to erase the information. Okay. So, now I can say this coercivity is not large enough to retain information. Okay, on the other hand, you take any contemporary hard disk drives, you buy a hard disk drive, the coercivity of your hard disk drives, I mean the material in your hard disk drive, like this. Oh, yeah, it fell down. Since when? This slide or this slide? Okay. Is it noisy? Yeah? Is it okay now? Okay, thank you. Okay, so before the mic was off, I was talking about coercivity being long enough, or I mean large enough or not enough to retain the information. So, in the old credit cards, the coercivity is small. So, a magnet that you keep in your pocket may be able to erase the information. On the other hand, if you take any contemporary hard disk drives, the coercivity is around 6000 oersted. Okay. So, you notice that this value coercivity is much larger than, I mean this is not coercivity, the field generated by the magnets, which is around 2000 worsted. So, 2000 worsted field cannot erase the information of hard disk drive, which has a large coercivity. So, you can correlate this coercivity to storage. Okay. So, if coercivity is large, then that material can store information without getting erased. Okay. So, you can relate MRT, MR multiplied by thickness to readability of hard disk drive. Okay. When it comes to writing information, this saturation field is the one that determines writability. Okay. So, if you remember this morning we were talking about Stoner-Wohlforth particles. So, we talked about having one particle versus having many particles next to each other. Okay. So, I told you if you have only one particle, this particle will reverse the magnetization exactly at Hk. Okay. However, when you have many particles, I told you that the hysteresis loop will be a bit different, because each particle will have some internal field coming from the neighboring particles and so on. So, because of the interaction, your hysteresis loop will be something like this. Okay. So, some particles, I mean half of the particles may switch at values lower than the Hk, but around Hk you can ensure that all the particles have reversed. Okay. So, in magnetic recording medium, we use this term Hs, which is the saturating field. So, we are very sure that at this particular field we can reverse the magnetization of all the grains. Okay. So, here you are reversing magnetization of half of the grains, whereas at Hs you are reversing almost all of the grains. Okay. So, we should apply a magnetic field larger than saturating field to write information. Okay. So, we can say that the Hs is related to writability of information. So, this is for reading. Let me use another color. Okay. So, MRT is related to reading, coercivity is related to writing, storing, Hs is related to writing of information. Let us say your recording medium has a saturating field of 10,000 worsted, and if the electromagnet writer you have, it produces a magnetic field of say 20,000 worsted, which means you can write information onto this medium, no problem. On the other hand, if your recording medium has a saturating field of 70,000 worsted, and if your writer can only produce 20,000 worsted, then you cannot switch the magnetization of the material. Okay. So, Hs too large is not good, which means you cannot write information. So, you have some limitation in the magnetic field that you can produce with your writers. So, because of that you do not want too high saturating magnetic field. Yeah, okay.
longitudinal recording and this perpendicular recording they asked.
Okay, I will come to this point in a few minutes later. So far I am giving very simple picture. So, it is too early to answer this one. Let us do some questions now. Okay, majority of you are right. Okay, correct answer is 1. So, point D is related to remnant magnetization. So, I told you that the read signal is related to MR multiplied by thickness MRT. So, D is related to reading signal. Okay, correct. Next question is about point C. Okay, point C is okay, let me copy and paste the correct picture. Okay, you look at this one, point C. Okay, most of you are right. C is related to HS, saturating field, we learnt, and the saturating field is related to writability. Okay, so, this is correct answer. Next one is about point B. Okay, all of you are right. Point B is related to storing information. Okay, before we move on to the next slides, I want you to have a look at these things. So, on day 2 we learnt about substrates, right. So, these are the substrates that we use for hard disk storage. So, this is 95 millimeter diameter disk. So, this is the substrate used for the 3.5 inch hard disk drive, and this is the 65 millimeter substrate used in the laptop hard disk drives. So, 2.5 inch form factor, and this is aluminum. Okay, this is aluminum substrate and this is a glass substrate. Okay. So, glass is used because it is rigid, it does not cause any waviness, but aluminum does. Disk, if it is very thin and when you rotate at high speed, it can like cause waviness and it can cause crash of the disk. So, that is one thing I want you to have a look at, you pass around. Then secondly, we learned about target and magnets below the target. So, in this case I am showing you a target and the erosion profile. So, here we have symmetric magnets. So, because the magnets are symmetric, you can see a large portion of this target is eroded and we cannot use it anymore. Okay. So, that is one thing I want you to have a look at. The another thing that I want you to have a look at is like you can use this sensor to look at the magnetic fields produced by these magnets. Okay. So, this is the like large scale demonstration of magnetic recording. So, you have a disc that has magnets pointing up or down. So, you have different lights indicating 0 and 1. Okay. Okay, so, let us continue. So far I have been giving you a very simple picture that we are going to rely on this magnet arrangement to store information, and we are going to look at pulses produced by these fluxes in the rate sensors for reading information. Okay. So, this is okay if you are talking about big magnets at very low density. However, in the state of the art magnetic recording, I asked you a question, how long is one bit, right. So, currently our bits are like only 12.5 nanometer or smaller. Okay. So, each line that you see here, they are so close. Okay. We cannot use in this case I collected this picture using magnetic force microscopy, but in the state of the art recording technology, the bits are so close I cannot take MFM picture. Okay. So, because the bits are so small and the data is tightly packed, the signals are messy and they are so messy that the signals are almost analog. Okay. So, here in the earlier picture I told you that we have this means 1, no signal means 0, right. You can see very clear peaks, whereas in reality of the current technology, the signals are so messy that they are almost like analog. Okay. So, people do a lot of signal processing techniques to retrieve the bits, the binary digits from this almost analog signal. Okay. So, this answers the question asked by Moditma. So, in current state of the art technology, whatever discussion I made earlier are too simple. So, in reality, like the signal will be somewhat like this. Okay. Let us say this is time and this is the voltage picked up by the sensor. So, you will have something like this. Okay. So, as a human we cannot say which is 1, which is 0, but the electrical engineers and mathematicians, they are very smart. So, they have come up with signal processing techniques to make meaning out of this. Okay. So, they can convert this into ones and zeros, for example. Okay. So, they produce ones and zeros from this signal and pass to the computer. So, this is the realistic reading mechanism. So, all the reading techniques that I gave you earlier, they are for understanding, but in reality the signals are very messy. I am thinking how far I should go. Okay, let us do something. So far I was giving you a very simple picture that MR multiplied by thickness is related to reading, coercivity is related to the storage, and saturating field is related to writability. Suppose I design two recording medium. Let us say I design two medium with desired values of MRT, coercivity and saturating field, and whether they will meet, they will give rise to the same performance. Or not is the question. Okay. So, for example, let us say I have two medium A and B, MRT, coercivity and Hs are almost same, but let us say with the medium A I can achieve say 1.5. So, when I say performance, I am talking about how much information I can pack in a given area. Maybe the media A give rise to 1.5 terabit per square inch, media B may give rise to 1.6 or 2 terabit per square inch, something like this. Okay, so, you can see that the two media A and B I have made have almost similar values of MR, coercivity and saturating field, but the ultimate recording density that I can achieve in recording medium B is more compared to recording medium A. Okay. Why is it so? I told you that these three are the parameters related to the reading and the writing and storing, but still I notice that the recording medium A is inferior compared to the recording medium B. Why is it so? Why it could be so? I have not taught you, so you can tell any answer. So, when you do the hysteresis loop, what is the typical size of your sample? A few centimeter. Okay. So, maybe like 1 centimeter by 1 centimeter. So, you take a small piece of sample, do VSM, then measure the hysteresis loop. Okay. So, you are getting properties of this particular sample over a very large area. Okay. Whereas, what is the size of the bit I talked about? Is 12 nanometer. Okay. So, the bits are like 12 nanometer long and maybe like 48 nanometer wide. Okay. So, we are talking about bits that store information at this kind of sizes on one hand. On the other hand, we are talking about properties like MR, coercivity, MS that we measure from a large area 1 centimeter by 1 centimeter. Okay. So, these properties that we measure at this scale won't represent what we say in this scale. Okay. So, micromagnetically the samples may behave different. So, whatever property that we measured from the VSM, they are macromagnetic properties because they are measured in a very large sample, whereas the bits that we are going to talk about, they are in the nanometer scale. Okay. So, if you really want to see how this recording media that you made will perform at high densities, we need to look at information in nanometer scale. Okay. So, people measure this information at nanometer scale using a device called Spintronics. Okay, let me come back to that. Okay, before we go to that, so people don't just stop here. Okay. I mean, measuring these properties give you some idea whether your recording media A or B is good. Okay, if coercivity itself is like 1000 Oersted, for example, you can throw, right. You can say that this media is useless. Okay. So, you can use this to screen some property, but they are not enough. Okay. They are not enough. So, the people who make hard disk, they look at some more properties like signal to noise ratio, pulse width at 50% height, overwrite, thermal stability. So, many of the other criteria also needs to be looked at if you want to ensure that the recording media you designed works at high density. Okay. So, what made this recording media to achieve 1.5 terabit per square inch and this recording media to achieve 1.6 terabit per square inch is the difference in these properties. Okay. Signal to noise ratio, pulse width, overwrite, many of these properties gives rise to the fine difference between many different media. Okay, that is because so far I was giving you a very simple picture. So, I was telling you that we are using magnets arranged like this. So, I was using a very simple picture that one magnet stores one bit. Okay. But in reality it is not the case. In reality, when you have a hard disk is made up of sputtered thin film. So, we are using sputtering to make thin films. So, the thin film is a polycrystalline material. So, we have lots of grains like this. So, we have a polycrystalline material with lots of grains and we are using them to store information. So, instead of one magnet that I described so far, we are not doing that, we are using a collection of grains to store one bit. Okay. So, the information is stored in many grains. So, that is why we have so many other things that we need to look at. Okay. So, when you do, I mean when you measure coercivity, all those things over 1 square meter area, maybe the properties of A and B average out. Okay. But when you are going at a small scale at the bit level, how these grains are arranged, they determine the signal to noise ratio and so on. Okay. So, if you take a hard disk drive, we have bits. So, if you zoom in the bits, the information is not stored in one magnet, but it is stored in a collection of many different grains. Okay. So, each tiny grain is like a one magnet. So, we are using a collection of magnetic grains to store information. Okay. And when you have a polycrystalline material, these grains are supposed to be random, right? You have no way to control each and every grain. Okay. So, there will be some easy axis dispersion or the grain diameter dispersion and so on. So, as a result we also have some issue like signal to noise ratio. Okay, just show me a hand, how many here are electrical engineers? 1, 2, 3, physics, majority is physics. Okay. So, the physicist may like wonder what is signal to noise ratio. Signal to noise ratio is something that determines how reliably the information can be passed from one system to another system. Okay. Let us take this room as an example. So, here the information is coming from my side to your side most of the time. Okay. So, whatever I produce is signal. Okay. So, this signal is coming to you. So, you are all very quiet. Okay. So, noise is low. Okay. The signal is reasonably high. Okay. Signal to noise ratio is high. So, you can listen to what I talk. Okay. Suppose we go to the Guwahati railway station, then I try to give the same talk, you cannot understand, because the noise of the railway station is so high that the signal to noise ratio is low. Okay. So, if signal to noise ratio is high, basically the information can be reliably transferred from one system to another system. If signal to noise ratio is low, we cannot pass the information reliably. Okay. So, that is basically a simple definition of signal to noise ratio. So, when we design a magnetic recording system, we want a high signal to noise ratio. That is one thing. So, we also want signal to noise ratio at high densities. Okay. It is not enough to have signal to noise ratio at low density, we want to have signal to noise ratio at high densities. Okay. So, I use this to show to my students. So, in some of my exams the students can bring cheat sheet. So, they can bring one A4 paper where they can write whatever they want. Okay. They can use that cheat sheet to write examination. Okay. So, they want to pack more information within this sheet, so they can cover all the questions. Okay. So, we just do not want to pack information, we want to pack as much information as possible in the hard disk drive. Right. So, like we do in a cheat sheet, we want to do the same thing. So, we want high SNR at high density. Suppose you write very small letters, but still you cannot make out, it makes no sense, right. So, you want to read the information from your cheat sheet, so that you can crack the examination. So, high density at high SNR at high density. So, this is what we want. Okay, in hard disk, whether in cheat sheet or hard disk drive, we want to achieve high density based on high signal to noise ratio. So, this is some example of the noise that we see in a magnetic recording system. So, I was showing you that the signals will be clean. Right? When I introduced you the concept of reading information, the signals are very clean, okay, but in reality you see this is the kind of signal we have. Okay, we have some signal, then you see the noise, even the peaks which correspond to the signal, they have some noise. Okay. So, this is what we get in reality. and this is at low density. So, here basically 18,800 bits per inch, whereas in current technology we are storing information at 2 million bits per inch. This is the kind of density at which we are storing information in the current hard disk drive. This is one example that I measured long ago. In 20,000 bits per inch itself, you can see so much noise, right. Imagine packing even more bits closer to each other, you will see more noise. Okay. So, we have to measure the signal, we have to measure the signal, we have to measure the noise, we can measure SNR, all these things we use a device called a spin stand. So, in this spin stand we have a motor that rotates. So, we place the disc. So, this is the disc you see here, this is the disc, and on the disc we can bring read write head. So, this read head write head will write information and read information. So, we can read the signal, we can measure the noise, we can measure signal to noise ratio using this device called spin stand. So, this is like a prototype hard disk drive. So, it is on a bigger scale. So, if your hard disk drive is like 1/4 of this size, this device occupies like this much area. Okay. So, it is a prototype bigger hard disk drive, where we can place our disk and read, write and measure the properties like signal, noise ratio and so on. Okay, so, now the disk is rotating and the head is reading, writing information. So, you can see the plot of measured data. So, in the one side x axis is a time, in the y axis you have the voltage. The sensor converts the magnetic flux into voltage, and that is what you saw. So, the pulses like this. So, this is coming from a perpendicular recording disc, where the magnets are like north south. Okay, now the density is higher. I am packing more density. You see the width is getting smaller. You can see more pulses now. Okay, I will play this again. Okay, so, in this picture x axis is the density at which I store information and y axis is the signal to noise ratio. So, that graph you saw something like this. Okay. The signal to noise ratio keeps getting lower and lower as you pack more and more information closer to each other. As you increase density, the signal to noise ratio becomes smaller and smaller. Okay, for example, I talked about two different media, right, A and B. So, let us say I place the media A and B in the spin strand and I measure the signal to noise ratio as a function of density. Density means how many bits I pack in a given inch. Okay. So, as I mentioned before, we need some critical SNR. Some critical SNR is reliably required for reliable reading of information. Okay. So, if the signal to noise ratio is below this one, is useless, we cannot read information. So, above this we can read information. Okay, so, I placed disk A and B, then I observed that in A, this is the density I can, this is the maximum density I can use. Okay. Whereas, for sample B, the disk B, this is the maximum density. So, which one will I choose? Which one will I choose, A or B? B, right, because B helps you to store information at high density. So, people do measurements like this spin strand to understand how the signal to noise ratio changes as you pack information at different densities. Then choose the disk that gives rise to high density, I mean high SNR at high density. Okay, so, people do a lot of research to minimize the noise, increase the signal to noise ratio and keep pushing this further and further. Okay. For example, maybe in maybe few years ago, the disk were like this. So, every year people try to push the limits of the hard disk drive. So, they keep increasing the SNR at high density. Okay. So, there is a lot of research going on, but we will not go into those details. Okay. Okay, so, let me give a conclusion to the magnetic recording, because I do not want to go into the depth of this one. So, maybe like 2-3 minutes, then we can go for lunch. So, this is the concluding remarks for magnetic recording. So, we learnt about how do we write, read and store information in magnetic recording. Okay. Then we also learned how these properties are related to hysteresis loop parameters like HS, MRT, coercivity and so on. Okay, then we learned that just meeting this is not enough. We also need to look at many other complex aspects like signal to noise ratio at high densities. And so on. Okay. So, the researchers who work on magnetic recording try to work on these finer aspects. Okay. These are like some qualification, I mean earlier qualification. To give you some example, right, I see many papers on magnetism. Okay. People will study some magnetic material which may have a coercivity of maybe 10 Oersted, okay, but still they will write in the introduction that magnetic materials are useful for magnetic recording and all those things. Okay. So, when a material has 10 Oersted coercivity, you cannot write that kind of introduction, because 10 Oersted coercivity is totally useless for magnetic recording. Okay. So, we are talking about materials having 6,000 or 10,000 coercivity. Okay. And we are also looking at so many other aspects that determine how a magnetic recording technology will perform. Okay. So, people try to improve this signal to noise ratio, all those things. So, because of all these finer details, let us say you all saw a disk, right. So, the disk that stores the information. In the current technology, if you count the number of layers, there are many different layers. Okay. People use so many different layers to enhance the signal to noise ratio at high density and so on. So, there are many magnetic layers, non-magnetic layers with certain function, which is not scope of this particular course. Okay, there are so many layers deposited by sputtering. So, some of them are 1 nanometer, 2 nanometer, some of them are even like 0.8 nanometer and so on. Okay, there are about 20 or more layers. Okay. So far we were discussing magnetic recording as if we store information based on one magnetic layer, but in reality there are around 20 or more layers required to achieve high signal to noise ratio at high density. Okay. So, these layers are deposited in clean rooms of class 10 size, I mean class 10, I do not know how many of you know. So, class 10 means you take a small volume of space. So, within that space only 10 particles are seen. Okay. In this room, for example, there may be 50,000 particles in that volume. Okay. But if you go to a class 10 clean room, within that volume you will probably find 10 particles. Okay. So, people make all these discs in class 10 clean rooms using sputtering equipments that cost around 10 million US dollar. Okay. So, people spend so much money, so much technology to make the hard disk drive. So, when you buy a hard disk drive, you do not realize the sophistication that goes in achieving this particular technology. Okay. So, after doing all this, do you know what is the price in which the hard disk drive is sold for, one disk is sold for? So, after doing so much layer, so much research, so much physics, everything, one disk is sold at a cost of US $7, okay, of which the substrate itself is like $3 or $4. Okay. So, substrate itself is $3 or $4, then you spend so much research, then you make a profit of $4. Okay. So, we always say that this is the irony of research. Suppose you go to a shop, buy a frisbee, how much it is? A frisbee, right? Frisbee also is like $20. So, if you go and buy a frisbee, it's $20, it's just plastic, you mold it, press it, you sell it for $20 US. But with so much technology and physics that goes into hard disk drive, we are selling for just US $7. Okay, that is the irony of high tech industry. Okay, so with that we will end this one. We move on to the other topics from tomorrow. Okay, thank you. Thank you.
So what's this target? I mean,
This is a cobalt target. Yes.